Hello everyone, my name is Igor Hong. I am a fourth-year PhD student in CMU. In this video, I'm going to present our recent paper on near-optimal stochastic bin packing in large service systems with time-varying item sizes. This is in joint work with Professor Qiaoming Xie in University of Wisconsin-Madison and my advisor, Professor Weina Wang. Let me start by introducing the traditional model of stochastic bin packing in service systems. Consider the model of a data center where you have an infinite number of identical servers. Each server has a resource capacity M, which can be thought of as the number of CPUs on the server. The jobs will arrive over time at random time points and needs to be immediately assigned to a server upon its arrival to start service. During the service, each job occupies a fixed amount of resource, and the job will leave the system after a random amount of service time. The goal of the problem is to design a job assigning policy that assigns the jobs to proper servers, such that it minimizes the expected number of active servers in the steady state, subject to a capacity constraint on each server. Here, an active server simply refers to a server that contains any job. This model has been extensively studied in prior work, but we emphasize that it has an important limitation. That is, it assumes the resource requirement of jobs are fixed during service. In practice, it could happen that the job's resource requirement changes during service. Consequently, after you assign the jobs to servers, they could continue to grow or shrink. Sometimes, this could cause the resource contention, that is, the total resource requirement on the server exceeds the capacity. One can certainly avoid these complications by just reserving resource for the jobs based on their maximum requirement. But this could waste a lot of capacity if the job only spends a small fraction of time at its maximum requirement. So how should we efficiently perform stochastic bin packing for those jobs with time-varying resource requirements? Okay, to study this, we propose a new job model where each job is considered as a Markov chain. The Markov chain has multiple phases, denoting different resource requirements. There's also a special phase denoting the completion of service. Here is an example with 3 phases. With this new job model, our goal is still to minimize the expected number of active servers, but we allow a small amount of resource contention, as long as the cost due to resource contention subjects to a budget constraint. Our main result is that we construct a policy called the joint requesting server sigma bar star, and we show that under this policy is asymptotically optimal in the sense that when arrival rate scales to infinity, under this policy, the expected number of active servers is at most 1 over square root r order larger than the optimal value, where r is the scaling factor in the arrival rate that goes to infinity. Moreover, under this policy, the cost due to resource contention is also proved to be at most 1 over square root r order above the budget. To get our result, our main idea is to relate the original problem to a properly constructed single server problem, which will be much easier to solve. The single server problem solves for an optimal policy for requesting jobs on the server. Suppose the jobs can arrive immediately after the requests. Intuitively, such a policy captures the most efficient way that one can pack those time-varying jobs on the server under the budget constraint. Importantly, we show that there exists a correspondence between the policies in these 2 problems, and such correspondence allow us to convert an optimal policy in the single server problem to an asymptotically optimal policy in the original problem. Finally, let me give you a bit of detail of how we do the conversion. Let sigma bar star denote the optimal single server policy that's solved from the single server problem. And we will construct the policy for the original problem by just let each server run the single server policy and request the jobs. The requests are denoted by those cycles. The scheduler will just assign jobs based on the request in a certain way. The resulting system under this policy will approximate IID copies of single server system running sigma bar star in the sense of Gauss-assigned distance. For more details, feel free to visit our talk or read our paper. Thanks for your attention.